What the f is a neural network and what does it mean to train one? These are some of the questions I'm asked most frequently, along with, who are you? Why are you stuffing ketchup sachets into your pockets? And, sir, please would you leave this McDonald's? Those first two are valid questions. With the help of a spreadsheet and some twiddly knobs, we'll answer both. But first, something simpler. You might remember from school the idea of plotting a line of best fit. We've done an experiment and plotted some data and we want to draw a line through the middle of those points. This is a linear regression. You might also remember that the equation of a line is y equals mx plus c, where m makes the line steeper and c moves it up and down. I promise you that's as complicated as the maths gets in this video. Here we have some data and a line over the top of it. I've added some nice sliders so that I can twiddle the values of m and c until I get something that looks close to our data points. But you might be shouting at your screen, your line sucks. It doesn't fit the data well at all. The data's more of a U shape, not a straight line. Right you are. You might also remember from school that quadratic functions were U-shaped, so we could add an x squared term and try to fit that. Let's do that and see what happens. This is looking like it fits a bit better. We can be more scientific than just eyeballing it to see whether it looks good. For each data point we have, we can measure the distance to our model's line. This quantifies how crappy the fit is for that data point. Then if we take the average of those distances over all of our data points, we'll get a single number that tells us how crappy our model is. This is the mean absolute error loss. We'll calculate this and write it on our plot. Now when we twiddle the sliders, we don't actually need to look at the graph anymore. We can just check if our loss number goes up and down. This is handy because it means we can have high dimensional data. We don't need to be able to plot and eyeball it. We can just calculate the loss and let the computer do the twiddling. So far we have data, a loss function, and some parameters to twiddle. This is the core of any machine learning algorithm. But you might recall that we started with a line and then said, hang on, that looks shit. So we made it a quadratic function and that fit the data better. But we don't want this trial and error. What if the quadratic had looked bad too? Would we add an x cubed term? And what about after that? What if the data followed a power law or a sine curve or some funky combination of all of those things? Life's too short. What we'd really like is if there was some kind of function that was flexible enough to handle any shape of data. That's where this janky looking thing comes in. This is called a rectified linear unit, or ReLU for short. And it's essentially a line, but we flatten all the numbers below zero. But this non-linearity gives us some interesting behavior. If we took the equation for a regular line and added the equation for another line, the result is just yet another line. Boring. But if we take a ReLU and add it to another ReLU, we can make some funky shapes out of it. If we twiddle these sliders, we can make something that looks like a line, or a bit like a quadratic, or something more complicated. And if we kept adding ReLUs, we can make some really complicated shapes. In fact, with enough ReLUs, we can stack them up like Lego blocks to make any shape. And this is what the grown-ups call the universal approximation theorem. And this is what makes neural networks so powerful. It means that each neuron in the network is just this simple value, which is easy to calculate, just a line with negative values clipped to zero. But if we keep adding neurons, we can approximate absolutely any data at all, no matter how complex. We don't need to decide beforehand whether we want a linear model or a quadratic model or anything else. We just create a model with a bunch of neurons with some random weights, throw some data at it to calculate a loss, then twiddle the weights to minimize the loss. Let's look at our trusty spreadsheet to see this in action. We'll start with a linear regression to show how it's basically the same thing going on, whether you're using a simple linear model or a complex neural network. The data we're using is the Kaggle Titanic dataset. We've got some attributes of each passenger on board the Titanic, and we want to predict if they survived. A bit morbid, but this is the first dataset that most people learn on. Machine learning people are weird. We'll use 3 features from this. Passengers on board the Titanic could be first, second, or third class. So P class is 1 if they were first class, P class 2 is 1 if they were second class, and if both are 0, they must have been third class. Likewise, they have the sex of every passenger on board. It was either male or female. Not very inclusive, but it was 1912, so I'll look past it. Again, we can encode this as a number, 1 for female and 0 for male. We also have this column, which is always 1. This acts like the plus c term in the equation of a line. We have a weight corresponding to each feature. The model makes predictions by just taking the values for each passenger, multiplying these by the weights, then adding them up, and we do that for every row. The loss column is then the difference between the model's prediction and the true value. The overall loss is the average of all those losses in the column. Now, we can twiddle the weights up and down to decrease the loss. We are training the model. Switching to a neural network, it's almost identical. The input data is the same. We're going to have 2 ReLU neurons, so we'll have 2 rows of weights rather than 1. The ReLU value of each neuron is very similar to the linear case we've just looked at. We multiply the passenger values by the first row of weights and add them up like before. The ReLU then just says, if that value is negative, replace it with 0, and that's the first neuron. The second neuron is exactly the same thing, just using that second set of weights. The overall prediction then adds those two neuron values together. And just like before, we can calculate the loss per row, average that to an overall loss, and then twiddle the weights to minimize it. Because we're using multiple values, the model can now learn non-linear patterns in the data. We've created a model with 3 input neurons, 2 hidden neurons, and 1 output neuron, and that's all there is to training it. If we wanted to create a more complex model, we could do the exact same thing just with more layers. So if you ever come across a machine learning nerd trying to sound impressive by saying that they train models, you can give them a knowing look that will pierce through to their very soul. And really, that's all I ask for.